Good morning. Welcome to today's webinar. My name is Beth Capellas, and I'm the Sales and Support Manager here at Triangle Microworks. Thanks for taking the time out and joining us today. Triangle is hosting a free multi-part training series called 60-20-50 Hands-On Training. Today, we are presenting Part 3, Communications in 60-20-50, MMS, GOOSE, and Sampled Values. Future training modules will cover topics such as bottom-up versus top-down 60-20-50 engineering process, testing, commissioning, and virtual isolation, and several more. You can find a full list on our website. Each training will be followed up with a companion lab exercise to help reinforce the key concepts that we introduce in each training session. We will also provide extended trial licenses to the tools that you see in each training to complete the lab exercise. Once complete, you can submit the completed exercise to Triangle for review and are eligible to receive a certificate of completion. If you'd like to be notified of these future trainings and lab exercises, please answer the survey at the end to receive notifications. Now, Part 1 and Part 2 were previously held over the last couple of months. If you missed it, no worries. You can find the recordings on our website under 60-20-50 Hands-On Training. I will drop a link to that in the chat during the webinar. You can find the videos and reference documents under handouts in the webinar toolbar as well. So with that said, I'd like to go over some housekeeping items before we kick off the training. The training is scheduled to be 90 minutes long. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. Please don't wait until the end. We will begin answering questions online as we have several engineers monitoring the questions and responding to them directly. We do have a lot of material to cover, so we'll most likely save questions for the end. Your best option is to submit them online, where you should receive a direct response. But if we do have time, I will try to take some breaks and read the questions to the audience. So with that, I'd like to introduce the folks behind the scenes answering the questions. Today, we have with us Jim Coates, President of Triangle Microworks, Christoph Brunner, President of IT for Power, and Eric Favre, Senior QA Tester. Next, I'd like to introduce our speakers. We have with us today Jackson Moore, Digital Substation Specialist at Triangle Microworks. Jackson received Bachelor's of Science degrees in both electrical engineering and computer engineering from North Carolina State University and has a background in power system engineering. Prior to joining Triangle, Jackson spent 5 years as a microgrid system engineer, where he designed and developed load management control systems for multi-source microgrids. Currently, Jackson works with our customers and development team to understand and solve the challenges our clients face. Next, we have with us Matt Green. Matt is a senior application engineer here at Triangle Microworks, bringing a decade of experience to the role. Matt serves as a technical trainer, providing direct customer support, conducting product demonstrations, providing one-on-one or group trainings, as well as hosting webinars. Additionally, Matt works as a quality assurance tester, specializing in the company's simulation tools and gateway. So now that you know everyone, I'd like to give you a little bit of background on Triangle Microworks. We were established in 1994 and have over 30 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their costs and development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field, and they are designed to troubleshoot, simulate, and automate testing for both a single device or a complete substation. Lastly, we also provide a SCADA data gateway, supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols as well as OPC. It's available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support SCADA protocols, like UCA Group for 62850 and DMP user and technical committees. Through our participation, we help define the protocols, we stay up to date on the changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Jackson to kick off the training. So with that, Jackson, I'll make you presenter.
All right, thank you, Beth. All right, so as Beth told us, the title of today's presentation is going to be Communication, specifically MMS, GOOSE, and Sampled Values. And as we've said, this is part of a multi-part series that we're doing covering IEC 61850. So we started in part 1 with a general overview of the standard, also comparing it to legacy protocols, point-based protocols such as DNP3, Modbus, and others, IEC 6870, 101, 104. In part 2, we took a deeper dive looking at the semantic data model that defines the data contained on our devices, and then the underlying SCL or system configuration language that defines that and actually is used throughout the engineering process. Today, we're moving forward and looking at these 3 different communication protocols that make up 61850. So I always like to start by kind of just doing that same overview. What is 61850? Well, it's not any one thing, and that's why we've broken up into these multiple webinars. I already spoke about that hierarchical semantic data model, those containers within containers, which allow us to intelligently describe the data that are on our devices. Of course, the communication protocols, which is what will be our focus today, client server, GOOSE, and sampled values. And then finally, the engineering process and the SCL that kind of permeates all throughout it. So 61850, it's not just a communication protocol, it's a lot more than that, although the communication protocol aspect of it will be our focus today. So I'll start out with a brief introduction. What is communication? What do I mean when I say this term? And we'll look at a couple different examples, see how it compares between humans and how the way that we communicate and how it is a little bit different when we talk about machines. And then we'll walk through each of the 3 protocols. And then finally ending with controls. This does ultimately fall under client-server communications, but we've broken it out into its own section at the end. So first, what is communication? Well, I'm communicating right now. When 2 people are speaking to each other, or in this case, even one, it's the method we use to share information back and forth to each other. So in the case of my voice, I think of thoughts in my head, I break them up into words, I arrange those words into a sentence, and then I use my vocal cords to send them out. A lot of these same steps are ultimately going to happen once we switch over to a traditional communication protocol. The person who's listening needs to be able to hear the words that I'm saying, decode them, understand them. It's certainly important that we speak the same language. In communication protocol terms, you might say a common namespace. If I'm speaking in French and you only understand English, then we're not going to be able to effectively communicate. So, just a couple of basic principles that are happening, whether it's me speaking to you or your phone sending a text message or a 61850 substation issuing a GOOSE message for a trip. Messages are always going to be exchanged between at least one sender and one or multiple receivers. For communications, messages need to be encoded and then serialized. So in the case of me, that's me organizing my thoughts and structuring them into words and sentences. And then finally, senders and receivers need to have a common understanding, shared semantics. So this could be agreements on grammar and word definitions in the example of me speaking, but in 61850, this will be a little bit different. Just a couple of challenges that we have to face when designing a communication protocol. It's quite easy when you and I are speaking to understand the context of my question. Say I'm speaking to my fellow application engineer, Matt Green, who's on the call today. He can easily tell based on the tone of my voice, my intonation, maybe the way I'm facing, whether or not something that I say is a question or a command. If we're talking about technical devices, IEDs in a substation, for example, we instead need to define explicit services. For example, read or operate, things like that. Next, we need to have a common language, as I've already said. It's quite straightforward in the case of spoken word or even written word, but when it comes down to machines, this gets to be a little bit more specific. We need to have that common namespace to know what, you can think of it like a dictionary, what words are we allowed to say, and so that we have a shared common meaning. And then also, what's the format of our words? It's not grammar in the case of a communication protocol. It's actually going to be things like, how long is the header? How do we initiate our conversation to begin with? And then finally, who is addressed in the actual message, in the communication that we want to send? Now, I can do this by looking at my colleague and saying a word directly to him, or maybe saying his name. But in the case of a communication protocol, we need to be a little bit more explicit with our address. So a couple quick words on terminology before we dive in deeper. So first, I want to start with client server. So client server is certainly a term that exists well outside the scope of 61850. But in our scope, it does have some specific meanings and a little bit of unique flavor. So in the case of 61850, a server is a device which offers its services to, crucially, one or more clients. In a similar way, a client is someone who requests services from one or more servers. So that's really the point that I want to drive home here, the or more. It's not a one-to-one relationship between a client and server. We can have a client that communicates with multiple servers and requests data from them or receives data from them. And in the same way, we can have a server that's sharing a connection and sharing data with multiple clients. So just an example of this to maybe make it a little bit more concrete. Say we have a handful of protective relays in our substation. These would commonly be referred to as servers in 61850 terminology, or IEDs. In this case, they could send data to multiple clients, maybe a local HMI, and also a local gateway that's passing data for offsite control centers. In the same way, these clients are communicating with multiple of those servers out in the field, different protective relays or devices interfacing with conducting equipment. So to contrast client and server, there's a kind of another paradigm that we can have for devices that are communicating with each other, and this is peer-to-peer. So whereas in client server, there's kind of an inherent hierarchy, peer-to-peer, everyone exists on the same plane, and they're just sharing devices between each other. So an example of this, bringing it back to a substation, would be those IEDs down at the bottom, those servers, which are all able to share GOOSE and sample value messages between them. For example, one IED might detect a trip, and he might detect a fault and issue a trip signal back to another device who's actually responsible for opening the breaker. These two devices are just peers to one another. Another way to think about this is vertical communication versus horizontal communication. So if you see this diagram over here on the right-hand side, you'll notice that I have all of my IEDs down here at the bottom. These are servers and peers that are able to communicate with each other horizontally, whereas they're all capable of sending vertical communication up to my clients here at the top. So client-server communications, sometimes referred to as MMS, which I'll be speaking about more in my next few slides, falls under this paradigm of vertical communication. Whereas peer-to-peer, this is where GOOSE and sample values will exist, communications that are sent back and forth between the different servers. So this is just a little bit more, as we step through, we've gone through our introduction, and now we'll be taking a closer look at client server in particular. So from a high level, client server is the SCADA protocol. It's the one that we're going to use to pass data from our IEDs or servers down at the bottom that are interfacing directly with our conducting equipment and performing the protection and automation functionality of our substation. Data from those devices will be aggregated into reports. They also might be read, in either case sent up to a client at a higher level for historizing, store it in some sort of historian database. Also, that's where we have our HMI, where we can see in a graphical way what's actually happening in our substation. And then also, finally, we can issue controls back down from that higher plane, from the clients, maybe to say, open a particular breaker. So of the three communication protocols we'll be discussing today, this is the one that maybe has the most similarity to other communication protocols outside of 61850 that have been common in the substation space for some time, namely DNP3 and 6870, 101, and 104, in the sense that they fulfill a similar role. So directory services. This is the first of a group of services that we have within 61850. Services, as I kind of alluded to before, are a way for us to define what we actually want to do in a given message. We can't just go out and request whatever we want. We have a set of tools in our toolbox, and each one of these services represents one of these tools, starting with directory. So this is one of the things that's a little bit unique about 61850, at least compared to some of the other protocols that I mentioned. Directory services allow us to go out and request, as a client, the data model from the server. Ultimately, as a client, you really only have two ways to learn about the device that you're communicating with. Either you provide an SCL file, which defines the data model of the server. This could be an SCD file that defines the data models and parameters and configurations of all of the IEDs in your substation, or it might be a CID or an IID that defines just a particular, or even an ICD, depending on what stage you're at in the engineering process. However, there is another mechanism. Instead of actually providing that CL file up to the client, you can instead just ask as the client, hey, server, please give me a description of yourself. And this is used using the underlying directory services in order to issue that request and then receive the description back. So in this example, the server is saying, hey, I've got two logical devices. This goes back to that hierarchy that we discussed in webinar 2. One is used for protection, one for measurement, and then I have a series of logical nodes, data objects, and data attributes on each one. All of that information can be passed up to the client and more. We can learn about what report control blocks that device is capable of sending, what GOOSE messages it's capable of publishing, so on and so forth. So this kind of has two applications. The one kind of more basic would be just for the client to go out, learn about the server, and then decide what information he wants to request or read, or what reports he wants to enable. Additionally, in a tool like TestSuite Pro, you're able to use this to compare the configuration that's actually loaded onto the server, discovered via the directory services, against an SCL file that you provide to your client. Basically making sure that the configuration that you're expecting, defined in the SCL file provided to the client, is what actually matches on the server. To give it a sort of a sanity check, let's say, if we look at this picture here, we see a picture of a house. This guy knows what house he wanted to build. Let's go ask the guy what house he actually built and make sure that the two align. So now, before we get into how data is actually transferred, let's just kind of set up a little bit of an example. So let's say we have a logical node, XCBR. As we spoke about last webinar, X in the logical nodes refers to an interface, and CBR refers specifically to the interface to a circuit breaker. Now, of course, this logical node will have child data objects, for example, position or pause. And that in of itself will have child data attributes, for example, SDVal. Let's say we want to find the status of the breaker by determining the value stored in SDVal, or the status value of that breaker. Well, the most basic way to do it is going to be to issue a read. When we do this, the client can go out and issue a request, and it passes a reference to the particular piece of data that it wants to request. So in this first example, notice that we've requested the entire pause or position data object, noting that this will have several children below it. Now, when we issue this read request, we actually do provide a functional constraint, or FC. In this case, our functional constraint is ST, or status value. So we're basically asking, hey, server, I want this particular circuit breaker, this data object under it, and give me all the data below it in the tree that has the functional constraint ST, or the status values. So this would include things like the STVal to let us know the actual position of the breaker, but also the T, or timestamp value, which lets us know the last time that that breaker operated, opened, closed. And then finally the Q, or quality, which lets us know, is there any reason I shouldn't trust this data? Are you as the server aware of any issues with the integrity of the data? Now we do have another option. We could issue a read to an individual data attribute. So in this second scenario, we've just gone ahead and asked specifically for the STVal or status value. But that's certainly not all that we can do with 62850, right? We're not just limited to reads. It supports event-based reporting. So in order to do this, the client's going to reach out to the server and establish a connection. And then as data actually changes, it'll be passed up to the server. So how does that actually work? Well, if we look at this example here, we have an IED represented by this large box, and on it a logical device and a group of configured report control blocks. Each one of these report control blocks has an associated data set. What is a data set, you ask? Well, a data set is defined during the engineering process, and it's a collection of data that I want to publish in a report. Again, notice here I've included Q1, that's just the name of a switch, X for an interface to SSWI. That's a logical node that contains information about a specific switch position. Well, a specific switch and the pause or position will tell us that position. And I've included the entire data object, and then I would also include a functional constraint here. Now note that I have this single data set linked to multiple report control blocks, and I might have a different data set linked to another report control block. Now, the reason I might have the same data set linked to multiple report control blocks is because while there's not a one-to-one relationship between clients and servers, there is a one-to-one relationship between a client and a specific report control block. At any given time, only one client can have enabled and received data from a specific report control block. Now, there are instances there are cases where you can instance a report control block, and in which case, the same report control block exists multiple times, kind of like what we have here with the same data set being passed into multiple control blocks. So just a little bit more about how that data set actually works. I want you to keep in mind that behind the data set, there's an entire hierarchical semantic data model that defines our entire device. So here we have just an excerpt from a single line diagram, a single bay, and then we have 4 different logical nodes over here referencing 4 different switches that we might have in this bay. So this exists in the data model outside of the communication. It's just a way of representing what's actually in my substation at any given point. And then as part of the configuration stage, I pick what data I want out of that data model and pass it into a data set. And then as we saw on the last slide, I associate that data set with a report control block. So what are the mechanisms for actually getting data, out of those report control blocks? Well, the first step is the client is going to configure the report control block. This effectively means enable it and reserve it. Say, hey, you're available. I want to go ahead and say that I'm going to be grabbing your data. Next, the most basic way, and this isn't really an event-driven method, but it will be a general interrogation. This is initiated by the client. And in that case, the server goes ahead and sends back all of the data in the report. You could think of this as kind of a cousin to the read that we spoke about before, because it is initiated by the client. And all data in the report, every single value in that data set, will be sent back to the client. So he can find out what the value is of everything at that given point. Now, this is in contrast to event-driven. In this next example, the event could be data change, something in that report changed, or it could be the quality of something in that report changed. In either case, the report is automatically generated by the server and published up to the client. In kind of a similar vein, we have cyclic reporting. In this case, we're not looking for data to specifically change. We're only waiting for a timer to expire. And after that timer expires, data is sent up from the server to the client. Now, one thing I should note in these event-driven approaches, only the data that changes is packaged in the report, whereas with the general interrogation, for example, all the data in the data set is sent. So using event-driven, aside from the fact that you just won't miss any data changes, is also a little bit lighter weight on the wire. So next, I just want to make you guys aware that there are two types of report control blocks: buffered and unbuffered. The difference is really somewhat self-explanatory by the name. An unbuffered report control block has no buffer, a buffer being a place that we can store events before they are sent out from the server to the client. Whereas a buffered report control block contains a buffer. So if communication is lost or interrupted, those events that might occur before communications are reestablished have a place to be stored and then can be sent up to the client. So before I dive in deeper on buffered reports, just a quick word about reservations. So basically, when you're designing your system, let's say as a substation engineer, someone who's actually responsible for the configuration of the SCADA communications, you have two options when designing a report control block. Do I want to reserve this report for a specific client? For example, let's say I'm designing a report that I know I want to be passed to my SCADA system, and a second one that I know I want to be passed to my local HMI or historian. I have the opportunity during the design phase to define reservations so that a specific report can only be enabled by one specific client. The other option is not reserved. It's a little bit of a misnomer, but it uses the term dynamic reservation in this case. The reason we still call it a reservation is because we still do get the benefit of the buffered reports. So effectively how this works is, let's say that I have chosen to have no reservations. All my report control blocks are available to anyone. And then I, as a client, come in and grab one of those report control blocks. Any changes that have occurred that are stored in the buffer before I connected will be passed up to me. And then some short time later, there's a communications interrupt and I disconnect. Now, a user-defined parameter, res v TMS, basically a reservation timeout, will start ticking down. Let's say it's 10 seconds. That report will still be reserved and held for me until that timeout expires. So if communications that time, no one else can grab it in the intermedium, and I'm able to receive all the changes that occurred that have been stored in that buffer. So this is not as relevant for unbuffered reports because there is no buffer to store it in. So a little bit more about buffering. There's really just a few possible states that a buffered report control block can be in. First, it could be disabled, in which case it's just sitting there accumulating reports. As data changes that's contained in its data set, it stores that information in a buffer, an entry ID indicating what that data is and when it occurred. During the resynchronization phase, this is when a client is actually establishing that connection, maybe for the first time or maybe after an interrupt. In either case, that's when the data is being flushed out of the buffer and sent up in a serial way up to the client. And then finally enabled. So in this state, the report control block is fully enabled, the buffer has been passed up to the client, and just as new changes come in, those are processed and sent up to the client. So of course, with any buffer, buffers cannot be infinite size. So there is an opportunity for a buffer overflow. The size of the specific buffer will depend on the manufacturer and the implementation, but ultimately they all are limited in their size and scope. So in this case, where we have a buffer overflow, a lot of data changes have occurred while no client was connected. Eventually the overflow occurs and the oldest entry is going to be discarded, tossed out of the buffer. Now, when a client comes and reconnects, the first message he receives during the resynchronization phase will indicate to the client that the buffer overflow has occurred. So even though there is a loss of data, there is a notification to the client, hey, while you were gone, I had to toss out reports because I ran out of space in my buffer. So what do you need to know about unbuffered reports? Well, not a whole lot that I haven't already told you. It's really the same. There's just not a buffer. Additionally, this means that there is no need to specify a reservation timeout. because there's not much point in waiting around for a client to reconnect if you don't have a buffer that you're saving for him. Now moving over to kind of a practical standpoint, what do you need to keep in mind? If you are going out, designing a digital substation, specifically the SCADA portion, the data that's going to be passed up to your clients, what do you need to keep in mind? Well, the first thing you need to do is decide, what data do I want to send? And this is the act of creating a data set. Now, as I mentioned before, you'll want to include data objects in that data set. This is a best practice, not a requirement, but it is definitely the recommendation to include entire data objects with a functional constraint. So when you do that, as I said before, you'll get quality and timestamp along with status value. The next thing you'll need to think about or deal with is deciding, when do I want to send the data? So commonly, you'll want to use data change and quality change. If any of the data in my data set updates, I want to know about it. That's the whole point of a report, event-driven scenario. There might be some cases where if you have analog data, you either want to do cyclic reports because that data is changing constantly, where no longer event-driven per se, but just every 3 seconds, send me the current, send me the voltage. Or you could still use a data change or quality change method and configure dead banding or limits. And then finally, you have to decide, who do I actually want to send my data to? Do I want to configure reservations? Who should those reservations be for? And then finally, don't forget about test tools. Please, as someone who works daily with a variety of 6150 test tools, when you're designing reports, design some extra ones in there. Think about not just what information do I want for my SCADA system, for my historian, for alarms. Excuse me, what information do I want to be able to pass to a test tool, maybe during commissioning or troubleshooting that might happen down the line. A couple more quick fields that I'll mention. So optional fields, this is where you can choose what information is actually going to be included in the report. For example, in the header, buff time or buffer time. So this doesn't actually have to do with buffered reports that we spoke about before. This is just if I'm doing something like data change or quality change. Let's say I have an initial change that comes in. Do I immediately want to send that data out, or do I want to wait maybe a fraction of a second and see if multiple other data points are going to change and then package all those up together? Ultimately, that's totally up to you. And then finally, integrity period. If I am using cyclic reports, this is the setting to decide how often I actually want to publish that data. With that, I'm going to go ahead and turn it over to Matthew Green, who's going to be using DTM and Test Suite Pro to visualize some of these concepts.
Hey, Matt, I'm going to make you presenter, and you should have the screen.
All right, can everyone see it?
Yes.
Perfect. Thank you, Jackson. So yeah, I want to go over some of the topics that Jackson's been talking about today and see what this might look like in some of the software or the tools you might use in a physical environment. So the first tool we're looking at here on the left-hand side, this is our distributed test manager. It's a little bit of a mouthful of a name, so we typically call it DTM for short. This is our system simulator, and today it's going to be simulating a bunch of servers that will be monitoring the electrical equipment seen here in the single line diagram. So with all of these values, you can see voltages on the voltage lines here. The currents can be seen on the transformers here. And if I simply just open a breaker, we can see this current's dropping to 0. And all of that information is then being fed over to the devices seen over on the left. Of course, as Jackson mentioned, with data changes or whatnot, that will trigger a change within the database, the data attributes, and will cause events to be occurred. So things like reports or GOOSE messages or whatnot will be sent out. The second software we'll be looking at today is the Test Suite Pro tool, and that can be seen here on the right. Our Test Suite Pro tool is our client tool for testing and diagnosing of events and occurrences within your system. So let's go ahead and start seeing what this would look like from the client side of the tool. To do that, I'm going to go over to the advanced client, and I'll be looking inside of IEV1 here. And so you have your logical device, all of your logical nodes. Then we can do something like go into the XCBR. The BR and XCBR stands for breaker. So if we go in there, we can see all the data objects associated with the XCBR, including things like blocking open and close and position. So if I go down to this and simply open the breaker here, we'll see the value doesn't change right off the bat. Well, that's because I don't have reports enabled, or I don't have any sort of polling or whatever set up. So I can right click here and perform a read. And sure enough, you can see the symbol next to it has now turned to a P. That is for polling. And we can see that the value is now off. But typically you don't want to have a engineer sitting here and just doing a right click and a read, or having your system continuously polling. I've done a read 2 or 3 more times since we started and nothing's really changed. We're kind of just wasting the bandwidth. So if I go ahead and close this back, I can go ahead and do a read and that'll all change. But let's go ahead and take a look at buffered and unbuffered reports like Jackson was talking about. So we'll go up to LLN0, which is a required logical node. And inside of there, we can see a data set. I have 3 different data sets inside of this model here that the server knows about. We've got the stat, that stands for the status values, and I can open that up and see that we've got the CSWI, so a controllable switch, status value, the position, XCBR, silo, all sorts of the functional constraint ST data sets or data is being used in this data set, as well as I have a measurement data set. Looks like a lot less, but that's because we're stopping at like the data object level here. So we've got our MMXU, that's our measurement logical node, MX, that's our measurements, and we've got amps and volts all stored within there. Now, a data set doesn't do too much unless you put it inside of a report control block, GOOSE control block, sample values, whatnot. So you'll see right under the data sets here in TSP, we've divided up the report control blocks into buffered and unbuffered. So if I open these guys up, you'll see the buffered report control block, BRCB, and then we've got stat. And sure enough, if you open that up, you'll see the data set being used as stat. We just made the names really convenient, so that way if you just see the name of a report control block, you know exactly what it is. And so the B at the beginning stands for buffered, and of course it is buffered, report control block, and then the data set name. As mentioned previously, we do have different trigger options for this. So we've just set everything for this specific data set here on data change, quality change, data update, integrity poll, general interrogation. And likewise, we have the measurement value here coming in at the measurements. Typically, when you're getting analog values, it would make more sense for maybe historical data to not be as important, which is why you can do some dead banning, or you can set up different ranges or whatnot. I went ahead and put this as an unbuffered just because I want to know when it changes for me to get that data, but historically I'm not too worried about that. So now if I come in and I go ahead and enable these reports here, what we will now see is if I come over and open this breaker, the current will drop to 0, the breaker of course opens, and we can go in and see those in the reports here. So as the data changes, I'm going to go ahead and grab a little bit more real estate over here on the right-hand side. You can see that the measurement and the status values here have been deployed to TSP via reports, and you can see it was due to data change. If you click on the individual report, you can actually see what was included in the report. So this specific report shows that the status value of the position has switched to off. Since we did receive this report, that allows us to keep the model up to date. I don't need to go down and do a poll. It is now getting this by report. And now if I go and close this again, sure enough, we'll see another report come across. You can even multi-select and see exactly what changed, and the model is kept up to date. Now, let's talk about buffered versus unbuffered. We're also seeing some analog values coming across, and you can see it jumping back and forth between 0, the breaker's open, there's no current, and 203, the breaker is closed, the current has resumed. If I was to say disconnect from this device due to a network error, or we had to restart the system or something, we'll see all of this go offline. We're no longer connected. And again, I can just toggle this breaker a few times. And when I connect back up, I'll clear this out to make it more obvious. If I enable this report, we'll see that we got the 3 messages that happened while I was offline. The 3 reports still came across. But when I enable the the measurements report control block, we aren't getting anything until the actual value changes while we have that enabled. So that's realistically what the reports look like between buffered, unbuffered, and polling. With that demonstration out of the way, I will pass it back over to Jackson unless we have some questions that are queued up.
Beth, do we have any questions that have come in?
All right, I will pass it back over to you, Jackson, and we can return to the slides, and maybe we could do a Q&A section a little bit later.
Sounds good.
Should be good to go.
Okay. All right, so now that we've spoken a little bit about client server, I want to go ahead and dive into the next communication protocol, which is going to be GOOSE. So we covered this a little bit, from a high level in our first webinar, but now we're going to be going a little bit deeper. So GOOSE stands for Generic Object Oriented System Event. Sometimes you'll hear that S as substation. It has officially changed as part of the standard and now stands for system. And that's, as 62850 applies to more and more applications outside of just traditional substations. So GOOSE is going to be the high speed and crucially peer-to-peer communication that's used for critical event messages. And this is ideal for things like interlocking, tripping, and protection schemes. So it is event-driven all the time, unlike reports where we have the option to issue reads or, cyclic reports, things like that. GOOSE is always event-driven. In fact, it's always being published. There's no acknowledgement of reception within GOOSE. It is a layer 2 protocol. You can think of it similar to maybe UDP, if you're familiar with that. But there are other built-in mechanisms to guarantee quality of service, namely the fact that it's repeated. And I'll get into exactly how that works here in a couple slides. But the bottom line, the thing that I hope you guys take away, if you haven't heard the term GOOSE before, is that this is a fast protocol that replaces copper wires by sending those same messages that used to go over a dedicated copper wire network, and now they're being passed over communications, right? So a lot less copper in the substation. Instead of having a dedicated wire for each signal we want to exchange between 2 devices, we now have maybe a fiber ring or some sort of communication network where we can pass these messages. So key term alert. So just like we had data sets for the world of client server communications, we also have them in GOOSE. There is one key difference, and that's really what I would like to point out on this slide. And that is that with GOOSE, we typically do not include an entire data object, but instead individual data attributes. So you might be thinking, what's the difference? If I have a position and I had a functional constraint of ST, what would be missing? Well, the answer in this example anyway is the time attribute. Because GOOSE is so fast, we're talking on the order of single-digit milliseconds, the time attribute is just not important, and it's seen as extra overhead to include it on the wire. So if I am notified within 3 milliseconds of a change, then do I really need to include the data set? I'm sorry, the timestamp in the data set. That's the general thought. So another key difference here that I want to point out is that I'm not actually any longer, I no longer have the restriction of having a single server subscribing to a single control block like I had in client server communications. GOOSE is multicast, meaning unless I do something to change the fact that it's multicast, it will be received everywhere by everyone. Now, when I say received, I just mean that it will make it, to the Ethernet interface on these devices. It doesn't mean that these devices will be configured to subscribe to them, but it is sent out everywhere on the network. So, let's just take a look at this as an example and see how it actually works. So I've got the same single line diagram that we looked at earlier, and I've got a couple different switch positions, which will come out of the data model of the IED that's interfacing with these different devices, packed into a data set. Now, those will be packed into a GOOSE message, which will be published out on the wire. And crucially, it will have a state number. I talked about how GOOSE has a built-in repetition mechanism to guarantee quality of service. State number falls into this category. So at my initial onset, when I start out, I have these different values telling me my switch positions, and I have a state of N-1. This will be published out onto the network, and any subscriber that is configured to receive this GOOSE message will grab the relevant data out of it. Now, a good thing to point out on this slide, it's very common to have extra data in your GOOSE control block, more than you need for any one particular device. Maybe the next device down the line cares about the first value or the third or the last one, but this particular device only needs to grab these two particular values. I can package all of that data up into a single GOOSE message, knowing that only certain subscribers care about some of it. Just something to note. Now, a short time later, one of my switches changes from open to close. This is reflected in the data model for my device, and within a couple of milliseconds, it's actually pushed out on the wire. And now my state number has incremented from N-1 to just N. This is now published on the wire, and the subscriber receives the updated data from this new message and includes it in its internal data model, which it needs to use for control functionality or protection, whatnot. Now let's dive a little bit deeper on what I mean by that repetition mechanism. So there's two relevant parameters that you need to take into consideration if you're designing a system that uses GOOSE. One of those is Tmax and the other is Tmin. And these both have to do with how fast or how slow the repetition will occur. So in the case of Tmax, this is the max time during a steady state. So let's say that no changes have occurred in a while. No breakers have opened, closed, that I have, their positions packaged into a data set. I'm now repeating at this interval. And this might be 5 to 10 seconds would be a common value for Tmax. Now, as a change eventually occurs, instead of waiting for this entire time, Tmax, immediately within that 2 to 3 millisecond range, I will publish that information out on the wire. And instead of again waiting for time Tmax, I now republish that information again at time Tmin. So that time will actually eventually decay. Instead of continuing to publish at that rapid rate, it'll gradually slow down until eventually we reach back to steady state. So what this results in is a flurry of messages clustered very close together in case one of them is lost sometime in transit. And then afterwards, as things settle down and data begins to stop changing as rapidly, we come back to this steady state that we had here. So a couple things to keep in mind. I've already talked about the fact that GOOSE is multicast. This means that it will be published everywhere on the network unless we do something to limit that. And the reason we would do this is basically for network considerations. And this is also applicable to sample values. I'm going to go ahead and talk about this now, but like I said, this is applicable to sample values that we'll be covering later. So there are a couple link layer attributes that are used to identify a particular GOOSE message that can be used as tools in your tool chest. So the first is the MAC destination address. This is just an alphanumeric string that identifies not so much the traditional destination, not a one-to-one destination address like we would have in TCP/IP communications, but instead, maybe you could think of it as a group address. Additionally, we have priority and VLAN that we can set. if we're choosing to use this in our switches in order to prioritize certain messages through some sort of intelligent switch, or if we're using virtual networks or a software-defined network. Also, another two tools that you have at your disposal are application ID and GOOSE ID. So GOOSE ID does need to be unique throughout your system. So if I'm publishing 75 different GOOSE messages across 25 different devices, then each individual GOOSE stream, if you will, needs to have a unique GOOSE ID. But this is something that can be set by you. It can be a string that makes sense to you, just a name that you can use to identify that GOOSE message later on. Application ID, also set by the user, but this allows us, if we choose, to group messages that are working towards some common goal. So maybe I have a group of GOOSE messages that are all trying to work together or are necessary to work together to accomplish a breaker failure scheme. I could assign them an application ID that groups them in that way. So these next two slides talk about how we can use first the MAC address and then next the VLAN in order to filter what messages are going where. So first we talk about doing MAC address filtering at the device level. So some, not all devices, include the capability to do hardware-based MAC address filtering on the IED itself. In this case, every message is still being published everywhere on the network, but then at this MAC address filtering layer on my device, I can very quickly and easily tell if a message is intended for me, because I know the MAC address of every GOOSE message and I know which ones I'm intended to subscribe to. So effectively what this does is it prevents the software layer from overloading because it's receiving too many GOOSE messages and trying to decide if they're relevant or not. Messages that aren't relevant are tossed out before they ever make it into the software layer. So here's kind of another way of accomplishing the same thing, but to use the filtering at the Ethernet switch. Now, in this case, you could use either VLANs or you could use MAC address filtering depending on the capabilities of your given switch. And you might do this, for example, if your particular IED does not support MAC address filtering. So there are a couple downsides to this. I would still say it's quite popular and widely used, but just a couple things to keep in mind. The first one is that you're probably going to be configuring a single port to have the relevant GOOSE or sample values messages passed out of it down to this IED. So that means if you come along and move this Ethernet or fiber optic cable over to a different port, you could break something. The other thing to keep in mind is that there's just a lot of extra configuration that goes into this, but this is an area that's changing rapidly. There's a lot of space being done by vendors who create switches in order to make this easier. Basically, a lot of the information needed to intelligently configure the switch is already contained in the SED file. So there's several vendors out there that are taking that SED file, reading out maybe the network topology, knowing which devices are connected where, and able to semi-automatically configure these switches to really reduce the burden on the substation engineers, potentially network engineers, whoever's doing that switch configuration. So now let's talk a little bit about, kind of like we did for report control blocks, what do you need to do? If you're someone who's coming in and designing a substation, designing the GOOSE in it, what are the things that you need to keep in mind? Well, first, just like we had for reports, you need to design your data set. What information do I need to accomplish my larger goal? What are my protection schemes? Who's responsible for detecting the fault? Who's responsible for opening the breaker? Make sure that I include the data in the data sets that will be needed in order to accomplish those tasks. And then include the relevant data attributes. And please include quality. And then assign them to GOOSE control blocks. Now, when do I want to send it? This was a very important question for report control blocks, but it's kind of shifted now that we're in the world of GOOSE. So in GOOSE, the data is always sent on change. So we don't have those trigger options that we spoke about before, like data change or cyclic. However, we do still need to keep in mind our min and max. A lower min time is typically reserved for more mission critical functionality. It will result in a higher network load, but there's a higher guarantee of quality of service. Now, a higher max time will make it less likely that I have a communications interruption and have lower bandwidth on the network, but it will also take longer before I do detect a potential network interruption. And again, common values for these are maybe 2 milliseconds for min transmission time and 10 seconds for max. Next, network considerations. So are my devices at risk of overloading because of too much sample values traffic or too much GOOSE traffic? This was I would say, a more common problem in the early days of 61850. Today, this really just depends on you and your application. If you've got a tremendous amount of sample values, then it's something that you might want to take into consideration. If you're working on a smaller system with just GOOSE, you might not have a problem. But yeah, these are things that you want to keep in mind. And then finally, just like for reports where we needed to decide whether or not we had reservations for a particular report, here we need to configure our subscribers. So this really, all of this work will be done in a system configuration tool or potentially an IED configuration tool, depending on your workflow. And this next slide kind of just shows you what the output of that is. So how you actually do the configuration will not be in SCL, system configuration language, what we see up on the screen here. It will be documented in SCL. You know, if you're using a good system configuration tool, this will all be GUI driven, but this is the net result. So we have two different, kind of cutouts here from two different parts of an SCD file. So this first larger one here is from the communication section of the SCD file. If you remember from last time, this is near the top of the SCD file or all SCL files and contains the communications settings for all the different devices in my substation. So here we're looking at the communication settings for one particular IED. Up at the top, we have maybe the more MMS level, the TCP/IP stuff like the IP address and gateway and subnet mask. But then down here, we have relevant GOOSE settings. So this is where the VLAN ID is stored, the priority, the target destination MAC address, and then it also provides a reference to the GOOSE control block. The actual GOOSE control block itself is just referenced here. It exists down in the IED section, a little bit lower down in the file. And here's what a definition of a GOOSE control block would look like. So you've got the name, you've got the data set, and then crucially, you've got the IED name of any potential subscribers. So ultimately, this is where the subscription is configured. And in a future webinar, we'll talk about XREFs. This just defines that this IED needs to receive the message. XREF or external references are where we define what data within that message that subscribing IED needs to receive. That's more of an application level discussion. So now I'm going to go ahead and switch it back to Matt, who's going to give us another demonstration, this time focusing on GOOSE and its applications.
Okay, Matt, I'll go ahead and make it here.
All right. All right, so as Jackson mentioned, a lot of the capabilities of your devices when it comes to GOOSE are all within the SCL file. Well, we use those SCL files to build up the Test Suite Pro or TSP workspace. In order to monitor and do the automated protection within the electrical equipment outlined in the single line diagram, there's a lot of GOOSE messages going back and forth, and a lot of devices rely on what typically in other protocols might be communicated across that copper wire. So how, as GOOSE is normally peer-to-peer or server-to-server communication, can we use a testing tool and a diagnostic tool like Test Suite Pro to monitor what's going on? Well, the first thing that we can do is we can take a look at the GOOSE tracker. The GOOSE tracker is just a combination of every file that you provided to TSP and all of the relevant GOOSE streams that are expected to be there. It will also let you know if there's any rogue or undefined GOOSE messages, GOOSE streams on the wire that it is seeing. So you select your adapter, whatever is going to the switch where the GOOSE is going to be distributed at, and then you'll be able to see, currently I have 18 different streams of GOOSE messages coming through. There are a lot of different columns. I have some of the more important ones for my use case grouped over here on the left side. But as you can see, there's a little blue divider. And as I move through this, you can see a bunch of different things, such as retrans drops or state number increments or whatnot. The most important header that I typically look like, column header, is this SCL wire match. And what that means is we want to make sure that the GOOSE that we're seeing is appropriate for what we provided TSP. So right now, everything says match. That means it's good. That means I told TSP I should see these 18 streams, and then we found those 18 streams. Everything's good. There are at least two different possible errors or warnings you can get from this. For instance, there is missing an SCL. And what that means is that TSP has found a GOOSE stream on the network that you're looking at, but you have no way informed it by providing it an SCL file on what that GOOSE stream is. It'll let you know, hey, I found this GOOSE stream on the wire, and I don't know why it's here. It's not part of the SCL file. That could be you forgot to add the SCL file, or you've got to turn off a device for another testing scenario, or anything like that. The alternative is if a stream is missing. So you tell TSP, I think there should be 18 GOOSE streams on the network, and you're only seeing 16. Well, that could be an indicator of you forgot to plug in your devices, or turn on your test sets, or plug in your devices that's actually doing the goosing. So this is just a good, very quick sanity check to make sure all the stream of GOOSE are out there that you're expecting. Now, in a similar manner to the report viewer, you can actually go over into the advanced client and look at the GOOSE control blocks. So if you right-click on them, you can subscribe to GOOSE. Even though it's typically peer-to-peer, server-to-server, TSP does allow you to subscribe to it through a client. And in a similar manner to the report control block, I will go ahead and get some of this. There's a GOOSE viewer instead of the report viewer. And in here, you can see every time that I've changed this breaker, I've gotten a bunch of messages here. But if I go ahead and clear this out and toggle out breaker again, generate some events, sure enough, we'll see a GOOSE message come across in the GOOSE viewer. And just like before, maybe I changed this a few times, I wouldn't so much expect to see the measurement values, the amps on this, because typically you want the status values. It's something that other servers can quickly perform an action off of. And so sure enough, if I select all of these guys, you can see the full GOOSE stream here, and you'll be able to see as the value is changing, just like you would in the report viewer. Now, importantly, what you might notice is that we're not just getting one on every single retrans. Even as we approach that Tmax here, we're not getting the state number 26, 26, 26, 26, right? Because that would just kind of fill up this whole display and make it harder to find the data that you want. So we'll only see the state number as it's increasing in here. Now, the retrans are used for the GOOSE tracker in order to make sure that we are still connected and we haven't had any sort of disconnection or a stream disappearing. So after we do that, we can see basically the values and update our model based on that. We can see what GOOSE streams are out there, and we can get values out of the GOOSE viewer. But in reality, this is not for TSP. The GOOSE is intercommunicating amongst all of my devices here. So how can Test Suite Pro actually monitor the communication between, say, like the SCU and the LPU? Well, that is where the signal flow comes in. The signal flow, as you can see here, allows you to track the flow of data across your devices. Anything that is in yellow, as seen here, is a GOOSE message. We have some light blue blocks here. These are our devices, whereas our darker blue inside, those are our logical devices. So what I can do is I'll set up the initial conditions for this test, and I will do a record on an entire event. So instead of just opening the breaker, I'm going to do something a little more complicated that will involve more devices and have them intercommunicate. I'm going to cause a differential fault on line 1. So I'll just simply click this red button here. The breaker will open, the breaker will close due to a reclosing function, and I will go back to Test Suite Pro and stop the recording here. So we can see a timeline has now been generated at the bottom, and this timeline will walk you through all of the communications that happened during that differential fault. So I will go ahead and click the next button. We'll see a differential fault is detected, which gets sent to the PTRC, which is effectively multiplexing all possible fault entries into it. And then the output of that will be this trip.general. The next step, we can see it's a yellow marker on this line. You can see the yellow line here is now goosing out. So the LPU here is issuing a goose message out to the SCU, which is receiving the trip general, and that's going to trip the breaker, which is why the breaker opened. And when the breaker opened, it's database updated. When it's database updated, it then needed to send a goose message out, and that is being delivered to our LPU and our BC, or our bay controller unit here. And then you can step through each of these individual events that happened and see where the communication is working properly or potentially where it is breaking down. And this will allow you to see how the devices are communicating with each other, despite you being a third party to this as a diagnostic tool. And the other tool I was going to mention for TSP is our GOOSE Publisher. Occasionally, you might need to issue a GOOSE message, potentially without a server. This can be used to replace missing hardware, to set up initial conditions for test environments where you don't have the ability to make physical changes to your hardware, or potentially to set up virtual isolation. So if you go to the GOOSE Publisher here, similar to the GOOSE Tracker, you would select an adapter where you'd want to publish this GOOSE on. Since TSP knows all of the GOOSE streams that you need for your system, we've been able to supply these and break them down by bay. So all of my line 1 streams in here to, we've got our transformer lines. So you can go in and see, just like this BCU, right, was publishing the op open and op close, you can go into that as a simulated stream here and see we've got our op close and op open, and you can issue by clicking the start button a publish of GOOSE without necessarily needing your server to be there. So those are some of the tools within our Test Suite Pro to monitor GOOSE traffic and even generate traffic. And at that, I will hand it back over to Jackson to talk about sampled values.
Okay, Jackson, you share the screen.
All right, thanks, Matt. Okay, so the next topic of discussion is going to be sampled values. So if you guys aren't familiar, sampled values is going to be the communication protocol that we use to transmit analog values. So think currents and voltages. In traditional substation, we have a series of CTs and PTs, current transformers and voltage transformers that are hooked up to different points on the line and then connected via copper wire to any IED which needs to perform some function based on those currents and voltages. Traditionally protection, but also this could be passed to metering devices, power quality, and so on. Much like GOOSE, it's going to be extremely fast and it's also going to be multicast, meaning that you can have many subscribers, but just one publisher. There's a key difference here. Well, several. One, it's not event driven. Anytime data is constantly changing as the waveform is fluctuating up and down multiple times per second. And it's just anytime a sample is taken, that's when a new message is going to be published. Also, synchronization is something that comes up a lot with sample values. Let's say that I need to subscribe to a sample value stream from 2 different points in my substation. Therefore, I have 2 different IEDs measuring and sampling the voltage and current there and publishing it. I need to be able to compare apples to apples to know that a message that came from one was sampled at the exact same point as a sample that came from another if I want to do something like differential protection. And we do that via a synchronization method via a grandmaster clock. So how does it actually work? Well, if you could imagine, if we zoomed in on an analog waveform and paused it and looked at exactly 1/60th of a second. I'm here in the US, we have a 60 hertz system. If maybe you're in Europe or somewhere in the world where they have a 50 hertz system, just imagine that this is that time frame. In that time frame, my typical sine wave is going to pass up, come back down, and rise again. So in that time, we're going to take 80 samples. In 1/60th of a second, we divide that up into 80 chunks and grab the value of the waveform at each point, resulting in a sample being taken every 208 microseconds. So we do this for not just one waveform, but 8, at least in a traditional 9.2 LE, and I'll define what that means in a moment, but a 9.2 LE sample value system. So we have 4 currents, or 3 phases, and neutral, and 4 voltages as well. Those are ultimately still coming in, from CTs and PTs. Potentially, it could be optical measurements or something like that. But somehow we're getting in those samples, passing them out on a network, typically fiber, over to any and all subscribers. And then I will also have a clock that exists on that network. Again, the clock becomes important when I have multiple merging units or process interface units. That's just the name for this type of device. When I have multiple of those on my network and I need to synchronize or harmonize the signals that are being published by multiple. So 9.2 LE, this is another key term alert. This is something that you guys are going to hear a lot. So when sample values kind of first came out, at least my understanding is that it was a little bit of the Wild West. And so they pared it down into a profile to make it a little bit simpler. And that is called 9.2 LE, LE standing for light addition. And it defined, I guess, a smaller subset, an easier way to use it. It defined that we would always have 4 currents and 4 voltages, and then that our sampling rate would commonly be 80 times per nominal cycle. Again, this comes out to 4,800 samples per second in a 60 hertz system, or 4,000 in a 50 hertz, every 200 or 208 microseconds, again, depending on your frequency. Now, there's also in 9.2 LE a definition for power quality, which ups that sampling rate to 256 times per nominal cycle, giving us 144,000 samples per second. Again, that's useful for power quality applications. So there is a newer variant on this, and that is IEC 61869-9. So both of these are sampled values, and I would say, in my experience, 9.2 LE is more widely available today, but 61869 is kind of the way that things are headed. So the key differences here are what I want to highlight. So the first one is that it's now user defined. What if I only want to measure current? What if I don't care about voltage? In that scenario, I can have a user-defined data set that says I only want 3 currents or 6 currents, but I don't want any voltages. Additionally, sampling rate is no longer tied to nominal frequency. There's a couple of recommended sampling rates for most protection applications. You'll be using this 4,800, which is the same number, you might notice, that we had in a 60 hertz system. So not a whole lot changed there. Another big change is the now user-defined support for including multiple samples in a single packet. This was already done in 9.2 LE if you were doing that power quality, where you would take multiple samples and package them together to ultimately result in less network traffic and less latency, better performance overall. But now I can, if I choose to, define that even if I'm just using my lower 4,800 samples per second rate. Crucially, though, it is backwards compatible with 9.2 LE. And I kind of want to explain what that means. So, this chart over here just kind of compares and contrasts. And this column right here is how we come up with this string that defines a specific 61869-9 implementation. So F refers to the samples per second. S, the number of ASDUs per sample value message, the number of samples that I want to include. So instead of sending out a new packet every time I take a sample, I could wait for 2 and then stuff them together and then pack it out. I and U, the number of voltages and currents. So what you end up with is a string that looks kind of like this down here at the bottom. And this would define a 9.2 LE system that is 60 hertz, F4800, S1, I4, U4. So a couple more just key considerations. Simulation bit, this is applicable to both GOOSE and sample values, but this is a bit that's in the header of a GOOSE or sample value message that indicates if this particular stream is simulated or not. Matt talked a moment ago about the GOOSE publisher. In Test Suite Pro, that has the ability to publish simulated streams, although you as the end user can choose to turn that off and pretend like it's not a simulated stream and it's a real stream coming from an actual device. SMP sync and synchronization source. So I talked about how time synchronization becomes very important. We use PTP, Precision Time Protocol clocks, very, very accurate clocks in order to synchronize all our devices to, so that we know that they're publishing in sync with one another. SMP sync allows us to specify if a particular message was synchronized to a local clock on the device or to a global synchronization source like one of these PTP clocks. It's common to have multiple PTP clocks for the sake of redundancy. We refer to these as grandmasters. So you might have multiple grandmasters, in which case the synchronization source can be used to identify which grandmaster you were synced to at a certain time. Again, these aren't necessarily considerations that you'll have to keep in mind when you're actually designing a sample value control block, but it's just something that I wanted you guys to be aware of. So what do you have to keep in mind? Well, if you aren't sure if you're using 92LE or 61869-9, then you're probably using 92LE. It's well established and it's supported by just about every vendor that supports sample values. So it's really just a matter of deciding which currents and which voltages do I actually want to include. I don't mean how many, I just mean if you look at the topology of your substation, decide where do I want my merging unit, 3 phases current and voltage plus neutral for each, and assign that to a specific sample value control block data set and control block. Again, just like Goose, we don't really have to make any decisions when deciding how often we want to send. Messages are always sent on sampling, and there's no T-min and T-max time like we have with Goose. Network considerations do become more important for sample values, even more so than they were for Goose. And we might want to take advantage of that MAC address filtering or some sort of software-defined network, use intelligent switches to decide what data goes where. However, if you are using testing devices like DTM or Test Suite Pro, you might need a port where all this data is aggregated so that you're able to use these test sets without having to move them around the substation to different points. And then finally, configuring subscribers. Pretty similar to how we did it with Goose, you're ultimately going to do this in a system configuration tool and just decide which devices do I actually want to receive this data, who needs it in order to perform their protection, automation, or control functionality. So lastly, before I turn it back over to Matt for one final demo, I want to just talk about 2 terms, process bus and station bus. So these are not terms that actually appear in the 6150 standard. You can download all the different documents from the IEC and you won't see these. However, they are quite pervasive in the industry. If you're attending conferences or reading papers, reading the Packworld magazine, you're certainly likely to see process bus and station bus. And so I just want to quickly define what they mean. They were confusing to me when I first came into this industry. So station bus is this orange box that we see up here at the top. It's a little misleading because technically these IECs down here might also communicate up with the HMI or client. But when you hear station bus, I want you to think client server communications like we already spoke about and Goose. When you hear process bus, I want you to think about sample values and a little bit confusingly also Goose. But if you hear process bus, it will include sample values. So why does this matter, right? Well, the reason is sometimes there's network segregation that occurs in substations where we have 2 different physical networks, one with process bus information being passed and forth. In that case, we might include all of our Goose on this network, and then certainly all of our sample values. And then we might have a separate network. Again, it might extend down to these end devices, but a physically separate network that we're using for client server communications. Now, if someone says they're only doing process bus, that doesn't mean that they're not doing Goose, and that's why I wanted to include this on here as well. It just means that they're not doing sample values. So again, it's a term that the industry has adopted, and I thought it was worth defining. So now I'm going to go ahead and turn it back over to Matt, who will give us a quick demonstration of sample values so that we can see that in action and see some of the functionalities of the tools in that regard. All right, Matt, you should now be presenter.
Yes, thank you. So just like GOOSE, sampled values is a publisher and subscriber relationship. And the publisher is the one that is monitoring the electrical equipment. So in this case, instead of looking at the previous GOOSE, we're looking at just the state of the breaker. We'll actually be looking at the CT here and looking at the amplitude of the current coming through. Typically, the publisher will be grabbing samples off the line roughly 80 times per cycle. And we can see that configured if we go into the publisher here and do a show model. You can go into that LLN0 where the control blocks are defined. And here is our sampled values control block. And sure enough, we can see sample rate is here at 80. So we're grabbing, we're sampling 80 times per cycle, and we're going to be sending that out to our subscriber. So for this example, I have a folder here for specifically for sample values. I have my sample values publisher and a sample values subscriber. This will allow the subscriber to accurately recreate the curve that the publisher has been sampling. So I'll go back to the electrical equipment here in the single line and bring up my sampled values. As you can see, we're pulling in the sampled values. I have it set to polling right now. And we're seeing kind of this curve coming in. Now, if I come and open this breaker, I have it set to stop on event change on this breaker. And you can see that several of the amplitudes, so if I hide the voltages here, you can see the current was coming down this line. The subscriber here was able to recreate the curve based off of the samples it was receiving. And then once the breaker opened and obviously the CT dropped to 0, we then lost that curve there and we're able to replicate the dead ending of that current. So yeah, sampled values can be used to monitor, the different phases of your amplitudes and voltages coming across the line. And this is just a very quick example on how you can see that in our simulator tool, DTM. And with that, I will pass it back over to Jackson, I think for controls and then for the wrap up.
That is correct. All right, you should be able to see my screen now. Okay, so yeah, we're gonna end with controls. So controls do, from a technical standpoint, fall under client-server communications. They are using MMS as the underlying, communication protocol to enable this. But I wanted to break it out because I feel like they kind of deserve their own time to shine. So when I say controls in 62050, I'm specifically referring to controls that are issued from a client down to a server. So in this example here, our client is saying, "Hey, please open gas insulated switchgear," and that's done via controls. So we'll start out with kind of the most basic example, which is going to be a direct operate with normal security, and I'll walk through what those terms mean in a moment. Starts out with an operate request initiated from the client. So from a practical standpoint, this is you clicking a button, from a control center, and the rest of this is just what's happening under the hood. So the server will receive this request to try and open the breaker. It will send back a response. Crucially, and this is a difference that we'll go into a moment here with, quote, normal security, it's just a response saying, "I have received your request and you're allowed to do it." And it will try and activate that output. In this case, it's a XCBR pause, so we're actually trying to open a breaker. There'll be a momentary, in-between state where the breaker is changing, and then eventually it will have opened and the action will be completed, and a report will be sent back to the client, letting it know, "I'm finished trying to do your requested control." Again, with a normal security, there's not actually any confirmation here that we actually opened, but I'll talk about that in a moment. So first, let's talk about the different variants. Well, first, this isn't much of a variant, status only. If you see status only on a control, that means that it has not been configured to be controllable. It could be controllable, but it's effectively in a read-only mode, and you as a client cannot actually control it. But let's assume it is configured for control. Well, there's 4 possible states, I guess, you could be in. So the first is direct operate, and then with normal security, select before operate with normal security, or these same 2 with enhanced security. So direct operate means I tell you to open, you try and open. It's pretty straightforward, like we just saw in the example a moment ago. Select before operate adds an extra step there. I first ask, I as the client ask the server, hey, is it okay if I kind of seize the controls? I want to make sure that no one else is trying to issue a control at the same time. Think of it like a reservation. The client, the server can then respond and say, yes, you are now in control. Go ahead, tell me what you want to do, passing the baton, so to speak. So that's the difference between direct and select before operate. Normal versus enhanced security. Not a huge fan of the term security that was used here. It's a little bit of a misnomer. The security that's used here is not, what we typically think of with cybersecurity. It's more security in the sense that I, as the client, know if my operation, my control was successfully executed. With normal security, as we saw in the last example, I know that my control request was accepted and that the the server successfully tried, but I have not yet received any confirmation that the result actually happened. In order to know that, for example, the breaker was actually opened, I would need to either issue a read like we spoke about before, or set up a report to contain the status value of that XCVR, that breaker position. With enhanced security, there is included in the response from the server whether or not that command was successful, and if not, why not. So these are the buttons you can push, so to speak, in a tool like Test Suite Pro, or even in a SCADA tool or HMI, although they may be abstracted away slightly. But select and select with value, I've already spoken about that. Cancel. Once I have selected a specific control and I have the authority to operate it, I can then cancel that, giving that up. And then finally operate, and a couple variants on operate, which allow me to actually do the task that I'm trying to do, issue the control. All of these first 3 come from the client, whereas command termination is a service used exclusively by the server to let me know either I've timed out with my select, or the control was completed or not completed. So just to reiterate, enhanced versus normal security. Enhanced security is used to supervise the successful operation. If I actually want to know that my device actually did what I was hoping that it would do. Whereas normal security includes no confirmation that the control was successfully carried out, only that it was accepted and attempted. And we kind of see this in action on this next slide. Some of you might be wondering, why would I actually do normal security? Typically, you wouldn't. You're really going to use enhanced security for most operations, really just for internal or local operations, things that are lower stake. That's when you would use normal security. So in this example, my client issues the request to open, just like we saw. Oh, I'm sorry, this is not like we saw before. Before we went directly to operate. Here we're requesting permission to operate it, reserving the right to operate this control, if you will. Once we get the select response in the affirmative from the server, we can now operate our breaker, requesting the output to be open. This part is shared between all variants. And then finally, again, shared between all variants, we see that a successful answer coming back from the server to the client, letting know that, yes, I actually tried, but it's actually this command termination request down there at the bottom, that last service that I spoke about on the last screen, that tells us whether or not my control was a success. And with that, we come to the end. So I bring it back to the first slide that I started with. What is 62850? I hope you guys now have a much better understanding of the 3 unique communication protocols that make up 62850. And I hope that you guys will, if you haven't already, watched our previous webinars and also attend our future webinars. We'll be diving into some more topics, including how to test and commission troubleshoot, and then certainly topics about the engineering process and how you actually can get into a system configuration tool. With that, I'm going to go ahead and turn it back over to Beth for question and answer time.
Great, thanks, Jackson. Let me switch over to my screen. Well, we just made it in time, so we covered a lot of material in 90 minutes. So with that, we will continue to stay on for anyone that would like to stay on and review some of the questions and answers. But before I shift over to that, I did just want to let everyone know, again, I put into the chat the web link where you can access the previous recordings for the trainings, part 1 and part 2. Part 3 will be posted there probably within a week. You'll also find the lab exercises for part 1 and part 2. If you fill out the survey that you'll be prompted with when you leave this webinar, you will get a follow-up email from me in which I will provide you with the recording, the lab exercises for part 3, as well as temp licenses for all the tools that you saw here today. So if you'd like to get that information, please fill out the survey. Give us a couple of weeks to put that together, and we will get that out to you. And of course, if you have any questions, you can always email sales@trianglemicroworks.com. So again, thank you for your time and spending 90 minutes with us going over all this material. With that, I'm going to shift over to a couple of questions and answers while we still have some folks on the line. So with that, the first question I'm going to ask, and Christoph, this is probably going to be for you if you want to answer, or I could read the answer, so maybe unmute yourself. First question, what is the use case of dynamic reservations for reporting? If report control blocks can only be linked to a single client at a time, are clients only able to access that report for a user set amount of time?
Okay, so should I take it?
Yes.
Hi, everybody. Okay, so basically dynamic reporting, a reservation of a report is when a device that has not been pre-configured to receive a report, like a test tool, there is still reports available, it can use that report for a certain time. And if we get reports like any other devices, the only thing it has to set the reservation time, which means if the device loses the connection, the report will still be reserved. When reconnecting, it will get events that have been stored. So it basically works like a normal buffered report. However, to prevent that the resource gets kept forever, when the device forgets to release the report, that's why we have to set that reservation time. So if I connect the test tool, I can use such a report, can do my tests, may disconnect for a certain while, but I should not disconnect longer than the reservation time I have set. So if I leave the substation, forget to release the report, it will be released later on. But in general, we recommend that you pre-design as well test equipment so that you don't use the dynamic reporting for test tools, but that you also allocate pre-configured reports for your test tools as part of the design.
Okay. Next question is going to be for you as well, Christoph. It seems that GOOSE messaging would mainly be used for binary type attributes. Is this correct, or is there a data exchange for more complex data types, for example, analogs?
Stating that it's mainly used for binary is correct, but as you say, it can also be used for analogs. There is not so many use cases. I have seen a few as an example when in a bay controller or in the protection devices, the RMS values are calculated, but the bay controller has a display that he wants to display them, then you could transfer them there with analog GOOSE. So it's possible to use analog values, but it's mainly used for binaries.
Okay, next question. What state number indicates in GOOSE message?
I can take that one. So state number, and I should mention its cousin, sequence number. So every time that a value in the data set associated with the GOOSE control block changes, the state number will increment. So let's say we start up, our device for the first time. We start at a state number of 1, and that repetition mechanism that we've talked about kicks in, and we kind of reach a steady state. Every subsequent message while we're in that steady state will have an incremented sequence number, but the state number will not increment until some value in that data set changes. So let's say a breaker opens, we send out a flurry of messages, each one of those messages with an increasing sequence number, but the state number only goes up once. Hopefully I didn't overcomplicate that, but hopefully I answered that question.
Okay, next question. I'll just open it up to everyone on the line. Can GOOSE message be unicast instead of multicast?
Well, there is a routable variant of GOOSE, sometimes referred to as RGOOSE. RGOOSE still uses a UDP multicast address. However, meaning in theory, you could change that target address to be a specific, traditional IP, in which case it would be unicast. But that's not layer 2 GOOSE. That's done in typical substations.
Okay. Next question, and this kind of opens up the door to a future webinar that we will be having. What is the difference between simulation mode and test mode? So I can open that up to either Jackson or Matt or Christoph. I know you answered it online.
Yeah, I mean, I can add, some information, and people have more to add later, that's fine. I mentioned this offhandedly when I was talking about the GOOSE publisher. And the reason you would want to use the simulation mode, it's effectively just a flag in your GOOSE stream that says, I am not the actual device. You might want to decide whether you want to listen to this stream versus the actual device's stream. Well, I guess technically it could be the actual device also publishing that stream, but it's typically sent out in a way to let devices know, I am in a testing mode right now. These should be used for testing, and it goes hand in hand with digital isolation, which includes things like actually blocking outputs to the electrical equipment, as I was displaying in the single line diagram. So you might send a phony or a simulated stream of data that says, open the breaker, but you don't actually want to cut the power off to a neighborhood or a hospital or something.
Okay.
Maybe
Go ahead, Christoph.
Maybe I can add a bit on that. So specifically the difference between simulation and test, as Matt just mentioned, the simulation is really the message. That means the message is coming from a device simulating something for a typical test purpose. So this is on the message base. The test mode and the test bit that we then have, that's more on the signal level. So that's more on the application level. That means this data has been produced by the device that is under test. So you may not want to use it for your real application. So as a simple answer, simulation on the communication level, the message, test mode on the application level, the signal.
Great.
And as Beth kind of referenced, we are going to do a future webinar specifically on virtual isolation, which will dive much deeper into these concepts. So definitely come back for that one.
Yep. I was going to mention that as well. So if you're signed up to get these notifications, you will receive an update on when we're going to present that. And the last question that I'll wrap up with, we did get several requests online with the Q&A to demonstrate something a little bit more specific related to what you were seeing here today. Unfortunately, we really didn't have time to veer off from our agenda. However, we are happy to take a deeper dive and a demo in any of the tools that you've seen here today. I think someone asked specifically to demo how Routable GOOSE works in Test Suite Pro. Please just feel free to email sales@trianglemicroworks.com, and we can set up some time with you and certainly take a deeper dive in the tools and a demo of something that you saw here today. So with that, I'm going to thank everyone again for attending. Hope you fill out the survey, and we look forward to seeing you at the next training session. Okay, thanks everyone.
Thanks.